Donc on attaque la deuxième session de la matinée. Hein, donc on a vu un peu le volet, j'allais dire, architecture, le volet algorithmique. Et maintenant, en fait, on avait décidé au niveau de l'ORAP de montrer qu'il y avait quand même des choses concrètes qui existent sur lesquelles on peut faire des tests, sur lesquelles on peut se faire la main. Donc on a la chance d'avoir deux constructeurs qui vont faire des présentations, donc Atos Bull et IBM. Donc j'en reprofite pour remercier Bull qui a été sponsor de cette journée. Et donc le premier speaker, c'est Atos Bull. Voilà. Donc on va attendre une mini-seconde le temps que les gens arrivent. Ouais, il faut appuyer. Mais j'étais jusqu'au bout les chercher. Donc on attend une minute et on attaque. Il marche pas?
Et est-ce que celui-là, il fonctionne? Ouais, c'est parfait. Et...
S'il vous plaît, on redémarre. Merci de regagner vos places.
Okay, just one more minute and I will start. Okay, everyone, thank you very much for joining. Quick brief introduction about myself. My name is Christelle Piechurski. I'm part of Atos since 7 years right now. I am in charge of supporting the HPC business within the North America and APAC region, and I'm also in charge of supporting all business relative to and product offer relative to the Atos Quantum Learning Machine. So today the topic of my speech basically will be to explain you what is the Atos Quantum Learning Machine that we have commercialized last summer. But before going and deep diving into it, I would like to go forward about what and why quantum computing and what is the Atos strategy that we are putting forward to address some of our future challenge. So you are all familiar with HPC, and HPC is basically helping tackling a lot of scientific complex challenges in various domains, like cybersecurity, like medical, like chemistry or weather forecast. So to be able to address these challenges, we will need in the futures to provide more computing capabilities, to say more compute resources, a larger and faster network, and more storage. But in the same times, we need to address some other challenges that you customers are facing, to say minimizing footprint and optimizing the energy power consumption of this extremely big machine to reduce the total cost of ownership of these big machines. So all these challenges need to put forward the limits of the miniaturization that we are going to discuss about. So first of all, let me come back on the an hardware issue that we are seeing more and more. So the race of power has been modelized by the Moore's law that you know all about, which basically stands that we are doubling the compute resources every 2 years, thanks, and this since the 17th, thanks to two things. The clock speed frequency increase, and both doubling the number of transistors and the number of cores that we provide on a die. But since 10 years and more than 10 years from now, we have seen some flattening in terms of frequency, and I'm pretty sure that you have all observed this when building a machine. And we have also, and the compute resources that we have been capable to provide to end users are basically now relative to the fact that we are capable of doubling the number of transistors and doubling the number of cores. But since a few years, we are also seeing some flattening at the number of cores, and the explanation is very simple. The fact that we are capable of doubling the number of transistors is relative to basically providing and being supported by a thinner manufacturing process. So a few years ago, this manufacturing process, for example, for the Intel processor was 32 nanometers. We are now moving to a thinner manufacturing process on the Intel Skylake processor, which is about 14 nanometers. And we are nearly, well, if we want to provide more transistors and continue increasing this computing capacity, then we will need to go to thinner manufacturing process, nearly to 5 to 6 nanometers. And at this size, we are nearly touching the atomic size, which could lead in I would say, which could end up with some strange behavior at the transistor level and dealing with wrong or bad results on the computing side. So this is one of the reasons we would need to, I would say, find an alternative computing power to classical computing. The second point is much more focusing on application. And we all know that the best, I would say, the blue sky supercomputer with unlimited number of resources would need billions of years to solve some of the specific algorithm that we find on the markets, like Anthony discussed about the cryptography. And in fact, if we take the cryptography, which is relying on the factorization, then we would see that the estimated time to run this algorithm is a 2 power of n. As soon as your n is increasing drastically, your problem becomes unsolvable on classical computer. So this specific algorithm, and not only cryptography, can benefit from quantum computing at that stage, and moving from classical computing to quantum computing will change would change from I would say exponential to linear growth in terms of execution time. And there is nothing magical about this. Anthony also discussed, and the two previous presentations discussed about them. It's basically because we have been capable of enabling new algorithms like the Shor algorithm in the computing world. By the way, we know that quantum computing, even though it would not benefit to all algorithms, is I would say, enough of interest to be a game changing on the market and to have the motivation to invest in quantum computing. Just a few domains of application where quantum computing can bring some boost in a 10 or 15 year time frame. So I already discussed about cryptography and most of the cyber security algorithms are relying on cryptography and on integer factorization. And thanks to the Shor algorithm, we have seen that we will get an exponential speedup. There are also some other domains like pharmaceutical applications that are relying and where we think that chemistry will be one of the domains where quantum computing will first benefit, just because of, I would say, the natural quantum properties. And this will lead to boosting the time to discover either complex or either the larger molecules that we have today. The two other domains that we think about is, the first one is big data and AI, so intelligence artificial, because these one are relying on the Grover algorithm, which has also been an algorithm enabling quantum computing worlds, and this will bring a polynomial speedup. And finally, you have over-domain like statistical analysis that it relies on the linear algebra simulation. For sure, there are much more domains than this one. This one are, I would say, the one that might arrive and might be the most of interest on the market. There are also other domains like oil and gas. There are domains like financial. There are domains also like aerospace or defense. Just to tell you a few words about where the community and the researchers spent their efforts during the last decades. So we have seen that there was quite a lot of progress in terms of quantum algorithm, for sure. But the over paradigm that industrial has been looking for is real qubit implementation, as for sure it's the real QPU that will make quantum computing being real on the market. And there have been a lot of efforts over the last 10 years that we have seen. We are, most of the time, the same question is coming, so when do you see a real quantum processor or ring quantum machine arriving on the market? This is a kind of tricky question, I would say. We know that fundamental research is going on since the 70s. We are now entering a design and prototype phase that may be for 10, 15, or maybe more years. It's still a question mark at that stage. What we have seen is a lot of announcements of QPU that are relying on several qubits that are now available in the labs. But I would say that there are so many constraints on the QPU, keeping the qubit coherent and stable. So that still need to be overcome to be pushed in terms of in a production phase and moving to an industrialization phase. There are several technologies, quantum technologies on the market. For sure, the leading ones, and we discuss about, are trapped ions or superconducting. There are other ones, like it has been named previously. And the purpose here is not really to compare the properties of trapped ion and superconducting. The purpose is really to stand that today there is not any standard implementation on the hardware sides, and this is something that is still undergoing. We still don't know what will be the leading technology to build, I would say, the standard of a general purpose quantum processing unit. So when we have said this, I would say that why don't we have a quantum computer today? There are, I would say, a lot of reasons, but the main ones are the ones that are on these slides. One of them is that the QPU systems need to operate at extremely low level temperature, near the zero to absolute, which would make quantum processing machines on your data center making quite a lot of an AV costly investment in terms of infrastructure. The second point refers to the fact that the QPU are quite unstable and the coherency lasts for only a few seconds, which makes the results difficultly usable. And the last one is that the QPU systems are really sensitive to the external noise, like electromagnetic interference or vibrations, which make the results not really reliable. However, the research is moving on, the research is progressing every day, and we really think that we need to prepare the end users and provide them the capabilities for anticipating their algorithm and make sure that they will be quantum ready when real QPU arrive on the market in a 10 or 15 years time frame. And this is typically the spirit that we have that have been put in building and designing the Atos quantum learning machine. So the Atos quantum learning machine is a quantum simulator that is provided as an appliance. So it has not, or there is no any standard QP implementation. Atos strategy has really been to invest on the software paradigm and building a software paradigm that would last for a long time in terms of investment. And this achievement is possible today thanks to both the capability of the Atos quantum learning machine to simulate up to 41 qubits and the furniture of the software environment that will run without the hardware constraint that we have previously seen. And this is very important as the, I would say, underlying hardware layout is relying on a genuine deterministic machine. Just a few words about the strategy of Atos in that domain. So I would say that the Atos strategy is a quite long-term strategy that has been established for the next 15 years. So with the ambition of Atos of being the first and the first European leader in the quantum computing, and maybe also enable this at overseas, and we'll see this later. What we have done is we've built I would say an advisory board build of work-life scientists in order to give proper direction to the Atos quantum computing and basically also to the Atos quantum learning machine. And in that sense, we also have an Atos quantum R&D lab, which is led by Cyril Alouche. I'm pretty sure that you all know Cyril. He is in this room too. And he and his team is in charge of supporting the quantum computing effort through the Atos quantum learning development machine. So a few words about the appliance. So the appliance relies on an in-memory infrastructure machine, basically that is capable of simulating up to 41 qubits, thanks to CC NUMO architecture, being capable of supporting up to 48 terabytes. It is providing with a software programming environment that I will describe later on. We do have also some optimizers, some simulators, and noise models that can be put on top of this, on the QPU interface to be able to simulate your algorithm. There are I would say several features that make the quantum learning machine quite unique. First, the Atos is providing its own Atos quantum assembly language, so AQASM, which relies on a universal and pure technology language that you all know, which is the open AQASM, and which make it very easily to implement whatever type of qubit hardware implementation. The second point is we do provide the capabilities to run hybrid simulation on this machine, which means that through an abstraction layer done in PyAQASM, so Pi for Python and a quantum assembly language. So the pattern will enable in your algorithms to run part of the code on the classical part and the quantum, the QASM part through the QPU interface to simulate the quantum algorithms. We also provide, I would say, some simulators. So most of on the market, most simulators that you will find will be the linear algebra simulators. When we started a few months ago, we provided the LINAG simulators. We're now providing the LINAG, the Fellman, the MPS, and the STABS simulators. The underlying hardware is very modular and scalable and can be delivered directly on premises. So modular and scalable means that you can start low in terms of simulating the number of qubits and decide to grow up your simulation capabilities by capitalizing on your initial investments. That means you start low, you add some building block on top, and you would be able to simulate a larger number of qubits, either to improve or to test the scalability of your algorithm, either to put more workload on your machine. We do provide an interesting features that makes our QLM appliance interoperable, and this feature is providing through an SDK interface, allowing customers to run their existing algorithm on top of the QLM. And at this point, we're supporting more than 20 languages. I would say some language that you know very well, like C, C++, but also over exotic language at that stage. And this is a quite very interesting features as you as end users, if you already, we talk about algorithm, but it could be also simulators that you are coming with, and we'll be capable on running them on our machine. It could be your noise modeling. It could be also some of the optimizer that some optimizer that we are going to see after. And then we are basically hardware agnostics. That means that if you customer decide to develop your algorithm on our Atos Quantum Learning machine, then this algorithm will run on every type of QPU implementation in the future. So, and this is possible thanks to first the fact that we rely on OpenChasm, and the second point is based on the fact that we provide optimizers that will be able to adapt to hold the whole QPU implementation that we find on the market. So a quick review on the Atos QLM offer. As I was mentioning, we start by simulating 30 qubits, and we can go up to 41 qubits. So 40 qubits was our next gen. We are now supporting up to 41 qubits. It is provided as an appliance, which means that we embed both the hardware and the software in that appliance, and we are capable of scale in terms of depending on your need on this one. A brief overview of our quantum learning machine software stack. So as I was discussing, we are providing a programming environment that you can see on the left part of a slide. The programming environment provide the AQASM, which is our Atos quantum assembly language. We do provide the abstraction layer, which is based in Python, and we'll see after this what is the workflow that we will be capable to handle. We have our own, and we provide our own compilers and decompilers based on a circ format, which is basically an interpreter of your circuit for sure. We do provide a set of quantum library through QLib. Quantum library, it's existing algorithm of library like SHORE, like QFT, that you will be capable to use directly without coding them neither in AQASM, neither in PyAQASM. We provide all the connectors with other frameworks like we already discussed. We do provide also some optimizers, so some optimizer, and one of them is Analyzer and Circuit Optimizer. Analyzer is basically an optimizer that would help end users getting rid of any topology constraints of different hardware QPU implementation. A rule-based optimizer basically will help optimizing the circuits depending on removing some sequence of gates within your circuits, and it also will help for you define a gate as a sequence of gates, depending also if your hardware is not supporting all I would say the usual gates, the usual suspect gates. We provide simulators, and the 4 simulators we have talking about. In the near future, will be also capable. So right now, if you want to find which simulator is better suit your algorithm or your circuits, you need to run simulator by simulator on your circuit. Later on, the purpose is really to provide what we call a sim optimizer and apply the most suitable optimizer to your circuit, depending on the depth of a circuit, depending on the kind of algorithm. We are also working of providing physical noise modeling, and it's a topic that it's very important to us. And the first physical noise modeling should come by the second half of 2018. They will first run on CPU, and later on in 2019, we will move the capabilities to run noise modeling simulation directly on GPU. So the workflow is really simple. Either you code your circuit in ACASM, if it's a very short circuit. Either, if it's quite long circuits, you could go through PyACASM that's directly embedded some of the functionality that ACASM does not. ACASM is, as I said, is a really pure language, so there is no subroutine, no condition. So it's quite linear code that you would have. PyACASM will help, I would say, shortening the ACASM file. Then you will need to compile this file through our binaries, and whatever type of execution you will run on top of it, either optimizer, either simulate your circuits, either noise modeling, you will apply it to the circ format. Circ binary, sorry. Just to go back to ACASM, so ACASM is really a low-level programming language for universal quantum circuits. We do provide the 13 usual gates that you may know, like Hadamard, CNOT, rotation, and more than this. And we also allows end users to define what we call custom gates. So you can set up some gates that are a combination of the usual gates. The PyACASM has two purposes, and I already discussed a bit about this, so I won't spend too much time on it. The first one is really to simplify the quantum circuits. As in ACASM, you would use the Python capabilities that ACASM do not have to embed loops, embed function of subroutines to make your code more readable. And it's also allowing hybrid simulations, so part of your codes can run on CPU, and the other parts can be simulated through our QPU interface. The circ is really an important part of our software stack because it's the, I would say, the pivot or the core of all the QLM software. So everything that you are trying, you will try to execute on the QLM will be applied to the circ formats that are generating through compiling any ACASM code. We discussed briefly about the optimizers. So the two of them that we're putting forward is the NNizer. So NNizer basically will help you, thanks to an import circuit and some, would say, a user-defined topology, will help your algorithm to run on any type of hardware by making the appropriate swapping for the nearest neighbors to communicate together. Then we have the rule-based optimizer that is basically done to detect some kind of sequence that you have, I would say sequence that you can find very often in one code. So for example, we know that a CNOT plus a CNOT is an identical operation. So all the CNOT plus the CNOT will be detected, and we will get rid of this sequence of gates. And we can, for some hardware, on some hardware, not all of the gates do exist, so we can, for some, we can rewrite some gate as a sequence of gates to adapt to this hardware. We got various simulators, as I was previously discussing, so LINAG, Feynman, STABS, and MPS. For sure, the most popular one is LINAG, but LINAG will give average performance, I would say, on more or less all circuits and algorithm, and as LINAG needs to store all the qubit states, you won't be able to get over some, I would say, over a certain amount of qubits. And then there are also Feynman. These tabs is for all concerning about code error correction. And in the future, we should have more simulators. Just speaking a little bit about our customers. So our first customer, and we are very proud of it, it's the Quantum Computing Institute led by, at Oak Ridge National Lab, led by Travis Humble. And I'm not going to iterate too much on this one because Travis is with us today. And he will give a pitch this afternoon, so I'll let him just talking about more for what they are doing with the Atos quantum learning machine. We have a pool of customers today. So overseas, we have the Argonne National Lab in Chicago. In Europe, we have now 4 customers. We have Surfsara in Netherlands, Jülich in Germany, the University of Reims, Urca in France. And our, I would say, brand new customer since last week is the University of Augenberg in Austria. This is my last slide, but not the least. I would say that quantum capabilities or being capable of simulating, of running quantum algorithm on a cloud-based system is crucial, but it's not enough. We all know that we are in a learning curve in terms of quantum computing. The expertise in that domain is very difficult to find. We're all part of the HPC world, and HPC is already an extra small world. I would say that quantum computing is an extra small world. So we really need, at some point, and this is my feeling, to invest and educate and train developers so they can be quantum ready in a 10 years time frame. And we do have that expertise at Atos. We can help and we can support you, but for me, it's an extremely, I would say, important key point. And that's it.
Okay, so one question, is your system sort of openly available for trial?
Oh, good question. Well, I would say that it's
for
really
non-commercial use.
It's a commercial use. So we are really commercializing it. But we offer some capabilities to have some and get some knowledge on our software environment by letting some of our prospect or customers, I would say, running simulation remotely on our machine, but it's not an open system. I would say that it's really on a base-to-base discussion with each customer or prospect.
And are you planning to open your system a bit for, again, trial and non-commercial use? Or?
I would say that it's something we are thinking of opening the ACASM specification. So this is one part. But for the rest, I mean, it's really relying on our infrastructure. So it will be quite difficult to do so, I would say.
Okay, and then I was encouraged to re-ask, or should I not? Re-ask my question as to can a quantum algorithm on a simulator beat a direct classical algorithm?
Can you repeat the question louder?
Yes. Okay, sorry. So imagine you have a quantum algorithm on your simulator.
Yeah.
Can this do better than a classical algorithm?
Right now, the purpose is not to do better.
I understand.
Right now, the purpose is really... So I would say that, and we had the question previously, it's something that we need really to focus on in the next months. There are a lot of customers trying also to understand if, well, what could be the boost? If there could be a boost, but being more concrete at application level to understand what we could bring to I would say, industry or academic in that domain, improve the quantum computing boost at that side. This has never something that has never been done. It's something that we are also trying to achieve. We have a lot of prospects and partners that are keen and are encouraging us to help them in that direction. So this is something that we might be able to answer in a, I would say, 1 year time frame.
Okay, thank you.
I have a minor remark.
Mm-hmm.
You have chosen to call this machine a quantum simulator.
Mm-hmm.
But a quantum simulator refers for now 15 years to a completely different object.
Yeah.
So as a researcher, I use this term every day. And it means something completely different, meaning a quantum system, a simple quantum system that simulates a Hamiltonian of another quantum system. And in our community, we daily use this term, and now you come with this classical machine that you will call a quantum simulator, that I would have called a quantum emulator.
Yeah,
and now
you're right.
you will introduce a confusion very soon in the community.
I think, yeah, so you're basically right. And we get these remarks, I would say, quite a lot of times. So at the very first stage that the machine has been introduced is what's called a quantum simulator. So all customers, our prospects come to us and say, wow, we want to learn about your quantum simulator. I agree, it's a quantum emulator, fully. You're right.
Merci Christelle.